Hi, Marilena.
Hi, Peter.
Thank you for joining the podcast Everyday Metallurgy. Today we're going to talk about a subject that has been requested by some of my followers. We're going to talk about microwaves in heating processes. I'm from the sintering industry, and in that world, microwave sintering has been a subject at conferences for many years. Every second year, a new presentation shows up, but the old guy says, "Oh, we have tried it; it doesn't work." But my feeling is that we never really understand, or we never understood what is going on. So therefore, instead of asking the same people who said we have tried it, uh, I would like to have a real expert that has been working with microwave for years and taking it from the microwave way instead of taking it from the sintering way. So that's why I invited you to enlighten us on what is microwave and how does it work if we look from the technology and not from the sintering side. But would you give a short introduction to yourself first?
Yeah, sure. First of all, thank you for inviting me in this podcast. It's really, microwaves, as you said, have been, my interest for many, many years. I'm trying to count in my head right now, but anyway, let me introduce myself and then we will do the mathematics together, right?
Yeah.
Uh, my name is Marilena Radoiu, and by background, believe or not, I'm a technological organic chemist, it's called. So I finished with this degree. It's an engineering degree from the Polytechnic University of Bucharest in Romania, where I did a master in technological organic chemistry. And after which I decided to do a PhD. And this PhD was in radiochemistry and nuclear chemistry. Now you say, well, there is not a lot of link with microwaves, but basically that's where I came across microwaves. In fact, I was working for my PhD thesis. I was working with electron beams, accelerated electron beams, which they come from an accelerator is called, and the whole structure of the accelerator is done with microwave cavities. So this is a master degree 1993, started my PhD just beginning of 1994. So this is a little bit when I started working with microwaves. In addition to this accelerator and the accelerating structure, which is something really, really quite, fantastic. At the time, just doing research for my PhD thesis, I came across people publishing on the subject of microwaves and organic chemistry. And I was like, really, wow, this is really new, it's not just a Bunsen burner or, an electric plate. So I started to get interested, and I was very lucky. One of the my colleagues, a female colleague, Diana Martin is her name. She was a specialist in this electron beam acceleration and therefore microwaves. So I was talking with her and I said, listen, I read this article, comes from Canada, and it was published late 86 or 89, I can't recall right now. And this guy, this professor in Canada, who tried some really cool microwave chemistry in a kitchen oven, and he blew up the kitchen oven. But I really like, the idea of not doing conventional chemistry. And she said, listen here, if you want that tomorrow, let's do it. So she went home. Her mother had a microwave oven, kitchen oven. Her mother was, not using it. So my colleague brought it to the lab and transformed it for me. She put a transformer on the table so the magnetron would run in continuous wave and different powers. And we made holes in the oven. And this is how I started microwaves. And I use a little bit in my PhD thesis. It was to do with plasma in my PhD thesis and electron beams. But basically, we at some point we combined microwaves with electron beams to reduce the cost of the electron beams. It was very successful. So we published a few papers. I finished my PhD thesis, and then I was invited to do a postdoc at the Academy of Sciences in Prague. One of the professors there also started microwaves, microwave catalysis, and he invited me to his lab to work on liquid-solid microwave catalysis, which I did for 1 year. And then I was like, I would like to, just have another experience. So I went to Canada, to Kingston University in Ontario, where I did a second postdoc, but this time in microwave plasma and microwave catalysis. So having that said, in Canada, it was totally different, not a really scientific environment, more to do with industrial projects. So I came across two very nice industrial projects, and that's when I made up my mind. I thought, I want to work in the industry. I don't want to stay at university. I like the scientific background, but I would like to put, this into the industry. So this is basically how I started to work in the industry. I was initially, my first job was working for BOC Edwards in England, where we created microwave plasma reactors for dealing with exhaust gases cleaning exhaust gases from the semiconductor industry. So all plasma, which became commercial. And then after about 8 years, I moved to France, where I worked for a microwave equipment manufacturer, as very, very small company, as their director of research and marketing and etc. Many hats on the same head.
All the hats.
Yes, all the hats on the same head, a small company. And I decided at some point to do an MBA. I was quite interested, as with my career was progressing quite a bit in commercial business plans, etc. So I wanted to do an MBA. So I took a gap year to do this MBA here in Lyon. And during the MBA, I kind of switched a little bit roads, and I thought, MBA, it's all about being your own, boss, creating your own business. So I created Microwave Technology Consulting in February 2018, and we are still there. We are dealing with microwaves for heating, but also for plasma. And what I would like to do and what my company is about is we are trying to close, this gap that has been created between academia, between scientific research and the industry. Basically, I see the microwave technology as a very good technology for industrial applications, but there aren't many. There are some, but not too many. So I am there to try, close this gap together, put all these resources together, because today, there is no such training, no such education, underground, not at all, probably a little bit postgrad about microwaves. So usually you have a postdoc or a PhD, you have a subject to microwaves, and that's how they start. But there is no basic education in that, which I believe is a shame, and I would like to change that as well. So that is about me.
Thank you very much. Should we jump into the technical stuff?
Let's do. I will try to share a presentation if you want me to do that. I'll share this. I think it's easier to understand if we have a few things. But once again, I like questions, and let's try to do this together.
Yes. Yeah. I'm curious to learn more about the fundamentals of microwave, because I think many people they really don't understand how they work and how they are formed, and therefore it's difficult to introduce, as you said, in an industrial environment, because if you don't understand it, could be afraid of it. What happens if it comes out?
Yes.
So, how does it really work?
Well, let me start with a question to you. Do you have a kitchen oven, a microwave kitchen oven?
Yes, I do. For heating food and making popcorn.
Perfect. And why do you use for heating food? Why do you use the kitchen microwave oven for food and not, gas or induction or?
Yeah, it's because it's fast.
It's fast.
Yeah.
Do you think it's also more secure in a way because you close the door and it's more like an oven than, open flame, or more contained? No?
Yeah, it is more convenient. You can heat the food when it's still in the plastic container. You don't need to make anything dirty and then clean up afterwards. So therefore, it's more convenient.
It's convenient. And let me ask then, do you find that when you heat up your food in microwaves, does it taste differently?
I don't think, no.
No. Are you afraid of cancer?
No.
No. Okay, because there is quite a lot of talk about microwaves, don't use your microwave oven because cancer, because it deteriorates, the food. And, sometimes maybe this is true if you don't know how to use it, if you overheat food, obviously, especially when it's contained, then yeah, it might deteriorate, some of the vitamins, some of the nutrients, etc., etc. So everything needs to be done correctly, right. Okay. Well, then let me start this presentation, and I will start with some basics of microwaves. So in terms of what microwaves are, they are electromagnetic waves, and that says quite a lot. An electromagnetic wave, it's a wave which is composed of the electric field, here in red, okay, and perpendicular to it, there is a magnetic field. And this is really, really very important in our presentation, because these two fields, they hit, okay?
Yeah.
And maybe sometimes only the electric field hits, maybe sometimes only the magnetic field hits, but maybe sometimes both of them hit. So it's very important to understand that, and it's very important to understand that in terms of microwaves, one of the parameters that actually sort of defines the microwave is the frequency of microwaves, okay? So the frequency also defines the wavelength. The frequency also divides the dimensions of the reactors, applicators, kitchen oven at home, etc., etc. So it's a very important factor in this, but it's also a very important factor in the what we can use in terms of industry, scientific and medical application, and even kitchen. So basically, we cannot use any frequency that's available out there. Why not? Is because of problems of interference. There are electromagnetic waves around us for different applications, mobile phones, Wi-Fi, broadcasting. So in order not to interfere with each other, there is this International Telecommunication Union, and they allocate frequencies for different applications.
Okay.
What I'm going to talk today is this ISM, which means Industrial, Scientific and Medical Application, ISM bands. And within this band, we have a few frequencies that I marked here in this table. The two frequencies that are nowadays used, and probably we will refer to them most of the time, is the L band, or the 915 megahertz frequency. Many people call it like that. And the 2.45 gigahertz, the S band, or this frequency here, which is also exactly the frequency which is used in the microwave ovens.
Yeah.
Now, these two for us are the most important today. Everything else can be also used, okay? I would also like from the very first beginning to mention that nowadays there are two ways of producing these frequencies here. It's either by the magnetron, which used to be from the very beginning. We'll go a little bit to the history of microwaves. It's either by magnetron, but nowadays, since about 10, maybe 15 years, we are also looking at what we call solid state, which is not a very good definition, but basically it's transistor, semiconductor-based generator. It's not a magnetron making the waves anymore, the microwaves anymore, but it's a transistor in there that makes them. Okay, both are very important.
Yeah. A question. The wavelength, when we talk 33 centimeter, I was told that the safety of a microwave in your kitchen is the small holes that you have in your door so you can look in. They are so small that the waves cannot come out because the waves are so much longer than the holes. So that's why it's safe. Is that the case?
That's exactly the case. Mind you, here there is a little error in my table because I should have said the wavelength in air, in free air. Okay, so if you have a magnetron, if you have a magnetron and you leave it in free air, that's the wavelength in the air. Now, in the waveguides, which we will see later, this waveguide is given also by the dimension of the waveguide. Okay, so waves, they propagate through waveguides in industrial application. In your kitchen oven, there might be a little waveguide inside, but you won't see it. Anyway, you have a window in the oven, and then the waves come through this transparent window, which is normally on the side, on the heavier side of the oven nowadays. It used to be on the top of it. Microwaves come in there, and they just go inside the oven, and the wavelength is not even important because they will bounce around the metal walls. Now you write the little holes, that in that metal grid, that's a metal grid with little holes, which are calculated as such as the microwaves, they don't go past them. So basically you have also a plastic shield or glass shield outside. That's mostly to do with steam or odor, but what keeps the microwaves inside is indeed the little holes. So the whole microwave oven could be done in that sort of grid if you want it, but no, you have 5 of the walls are metal and one is grid. Okay.
Yeah.
Right? Can we go?
Yes.
Yeah. Right. In terms of materials, I think this is also something that we need to understand, how materials behave with microwaves. So basically, we have three different categories of materials. The first category is a material that doesn't absorb whatsoever. You send microwaves through it, there is no absorption, no heating effect, okay? And we call it an insulator, or a material which is transparent to microwaves. And I gave a few examples. Quartz is one of the materials, PTFE, non-polar solvents, alumina. These are transparent. There are some others, but these basically are transparent to microwave materials. Then there is a category which is conductors. You send microwaves to it, but the microwaves cannot go past them. Okay, they are bounced back. Okay, they are called reflectors, and the best example here is metals. Okay, and there is absolutely no heating occurring in there. Okay, so no heating whatsoever. And then the materials which are quite interesting for microwaves, okay, these are the dielectrics. So material that absorb totally or partially the microwave, the energy of the microwave. They are also called absorbents. And in these materials, if you send microwaves, you will see a difference in temperature. okay, which
Yeah.
is very easy to calculate.
Hmm.
And as an example, I have water, liquid water, polar solvent, zeolites as solids, okay?
Yeah.
I would like to ask you to keep in mind this liquid water here, and we will go to the next slide, and then I will
Yeah.
ask a question.
Yeah. I'm also a little confused on the metal as not able to heat it, because that is what we are trying to do when we make sintering.
Ah, that's a very good question. Let's wait a little bit,
Oh,
okay?
cliffhanger.
Your microwave oven at home, inside there are metal walls, right?
Yes. Yeah.
I mean, it's not exactly the very good example, but in an industrial oven, okay, microwave oven, you will have stainless steel 316L. If it's wood, it's steel, which is non-magnetic, doesn't absorb whatsoever. So the microwaves from this metal walls, they if they are not absorbed by the sample, they bounce back,
Yeah.
and we can actually read this. We call it reflected power, so it's power which is not absorbed, so which could be 100% of micros, or it could be less, because you don't want to start an industrial oven at 100 kilowatt with nothing inside, right?
Yeah.
But just as an idea, usually these ovens, they use very nicely polished metal walls. We call them mirror polished. So the microwaves, they are not absorbed in the wall itself. And we'll get back to the sintering of metals later. Okay.
Yeah. Okay.
So in terms of how we heat, how do microwaves heat? But basically we have two direct heating mechanisms. One is called dipolar polarization or dielectric heating. I named polar molecules in there. Okay, and what it is there, let's try to imagine dipolar molecules. So one part is charged positively, so let's call red is positive, green is negative charge, okay? And these molecules, when you apply the microwave field, they start to move, because of the electric field goes plus, minus, and these dipoles will try to align, to go in the direction of the electric field. So plus with the minus, and that's but because the frequency is so high, and these molecules could be, it could be water molecular mass 18, or it could be ethanol, which is a bulkier molecule. Okay,
Yeah.
they can't move. They can't follow the whole movement of the electric field. 2,400 megahertz means that the electric field moves at 2,450 megacycles per second. So these molecules, they cannot rotate that fast. So they start to vibrate. But by starting to vibrate, they also hit each other, they align each other, they start hitting each other, and that creates the heat. So the energy is absorbed by them, and they are hitting. There is a similar, now if we have a second mechanism, is the ionic conduction or interfacial or space charge polarization. It's a bit similar, but now take into account that you have positive or negative charges. It happens exactly the same as the polar molecules. So they will try to go with the opposite charge of the electric field, and they will create this polarization and therefore heating. And because you mentioned plasma, I also wanted to because obviously in these two direct heating mechanisms, the heating mechanism depends on the charge of the molecule. But if your molecule is not charged, that means you cannot heat with microwaves, okay? So, and my question comes to, if your molecule is not charged or cannot move, you cannot heat it. And my question was about liquid water. So according to this mechanism, liquid water basically can heat up, okay, with microwaves, and this is what we do at home. But what happened with ice? If this water is solid, what do you think? Would absorb or would not absorb?
Based on what you just said, it shouldn't work. So
Exactly.
you should not be able to defrost.
Yes, that's it. This is why the microwave oven at home is very important, because it's being created to also defrost. So that means, you know, that when you put your frozen meal on that rotating plate, the rotating plate is made in such material that absorbs a little bit of absorbs microwaves. So if nothing absorbs, it absorbs the walls inside. They will absorb microwaves, and that will create, the air will heat up inside, and then that will be that heat will heat up your frozen food, and when the first liquid water molecule starts to form, that's when
then it starts.
Then it starts, and that also explains why it's so non-uniform, depending on how, the quality of the microwave oven, depending on many parameters. Sometimes it's not uniform. You cannot get it very uniform, right?
Yeah, that's right. You often have cold spots in the food.
Exactly, and you know, the manufacturer of the oven will tell you, you know, stop it every now and then, give it a stir, move it on the plate. So it's exactly to avoid this kind of problems and to increase a little bit uniformity. Okay, so basically these two mechanisms are direct mechanisms. But now, how can we heat up materials that do not absorb? We still want. So there is, I put here, is not very well known. So it's something that I'm trying to do, maybe not for the first time, but I'm trying to also make this more public. Why can't we use microwave excited plasmas to heat? Right? A microwave excited plasma at atmospheric pressure, for example, will go a little bit deeper in that. You can create a microwave excited plasma in nitrogen, which is an inert, argon, helium, any noble gases. You know, nowadays we all create also in reactive gases, but inert gases, you can create a plasma very easily. And this plasma at atmospheric pressure is quite hot, can go to 1,000 degrees. Now imagine you have a material that doesn't absorb microwaves. If you put here, this is a video, I will run it. So this is a plasma, so it's created inside the microwave cavity, and I left it go outside. It's nitrogen, and you can see this is in a fume room, so all is extracted. You can see that because it goes into the air, it makes it starts making some nitrogen oxide, so this reddish color. So, but if this all enclosed and this nitrogen, it's inert, and then you need to heat up something like ceramics in sintering, why can't you use this heat, right? So I call this an indirect heating of all materials, no matter of their dielectric parameters, no matter of the charges that are inside. You can heat anything with this.
Yeah. Is it like a hot flame?
Let's call it a hot flame, but it's more than that, and I will explain a little bit later why it's more than that. Basically, because you know in fact, it's like a plasma torch, if you want, but there are no electrodes in there. It's only the electromagnetic field ionizing the gas.
You're not making ionization of the plasma.
You have, in order to have a plasma, you need to ionize the gas. Okay, that's what we call. But there is a totally different mechanism to any of the torches using electrodes, etc. Okay. So let's go further if you don't have any more questions. Okay. So now I'm going a little bit to microwave sintering and a little bit towards the history of the sintering. So I believe that everything that we do nowadays with microwaves started with a kitchen oven. No matter if it's food related, no matter if it's chemistry related, and also sintering. I looked a little bit around and to see where was the first sort of record of sintering using microwaves, and that was probably late 60s by this Canadian, which is called Tinga. Okay, but most of the publications, they started from late 70s, and they came from the American Ceramic Society, they came from British Ceramic Society. And why was that? So if I go to the right, to these two tables, again, if I look at the history of the microwave oven, when it was sort of discovered and patents were filed by the American Percy Spencer, okay, until, about 20 years later, when Amana, I think nowadays they belong to Whirlpool or something like that, when Amana launched the first countertop microwave oven, that was 1967.
Wow.
So if you look at how this oven started to sell, it makes sense that everything that we started in terms of chemistry, etc., came in the years 1980s, late 70s, right? And 80s, there was a lot of kitchen oven, what I call kitchen microwave chemistry. I call it like that. So a lot of this, and there are, impressive photos of microwave ovens being exploded by the different chemical reactions, because everybody notices the same. If you try a reaction in the microwave oven, it's very fast. Now it's very fast also because as chemists, we know that when we do research, we try to work under safe condition with very small quantities. So when you put a small quantities of reagent in your microwave oven, and if you manage to start heating that, when you turn your oven on, your power will be something between 1.5 and 2 kilowatt in a tiny quantity. Okay, so no wonders that actually heats up very fast and can go to an explosion. Okay, so there have been many things like this, and blessing or curse microwave, the kitchen oven, helped us to advance and be where we are today. Now, about in terms of history of the sintering, until about 2000, the years 2000, the microwaves were applied mostly to sintering ceramics, which you will see a little bit later is not exactly the best thing to start with. These are non-absorbent materials. Most of the ceramics are non-absorbent by microwaves, so they are transparent. So nowadays, sintering is applied to any metal powder that you can imagine, and retained metal powder, it's an important little bit there, and any combination with metal, the metal ceramics. Okay. Right. I try to summarize this a little bit, the microwave sintering and how we can heat different materials with microwaves. So I started with ceramics. Once again, they are microwave transparent, so they don't absorb microwave as such. And as an example, I have here, sintering alumina, very dense, transparent alumina, zirconia, mix between alumina and zirconia. So these are metal oxides, which are transparent to microwaves. Then metal powders, okay. And because they are powders, in fact, they absorb microwaves. Okay? So it's not like a metal wall that you send your microwaves onto. Metal powders, in fact, absorb really very well microwaves, a little bit too well. Okay.
Yeah.
So, and again, in the literature, you have examples of what metal powders have been sintered with microwaves, and you'll find, steels like austenitic or ferrite, so austenitic 316L, for example, ferritic steels for 34L. I can't remember all this, but both of them are sintered in microwaves, and all sorts of tungsten powder is one of the most studied, and then all sorts of mixture between tungsten, nickel, iron. There are so many examples out there. And then the third category is the composites, where you can mix, these ceramics, transparent, with either susceptor, what we call a susceptor. It's a non-metal, if you want, material which absorbs microwave, and silicon carbide, beta silicon carbide is one of the example. And then tungsten carbide, it's another example, cobalt, and you can make any single mixture. So these are the three categories of materials, but how we heat them. So if we go to ceramics, I mentioned as an indirect heating method, microwave plasma. Can you heat ceramics with plasma? Yes, you can. I melted several alumina tubes with plasma.
Yeah.
Okay, and quartz as well, and many things. Not because I want it, just because the temperature was very high.
Was very high, yeah.
Yeah, And, and it's probably one of the problem when we think about microwave plasma is where to contain it, right? So it's one of the problem. And then you have direct microwave heating can be applied to composites and can be applied to microwave susceptors. And there is another method, which I call it a hybrid microwave method, heating method. I know in the literature, they call it infrared microwave, but basically what it is, they use this compact, it's called green if it's, ceramic green compact, or this compact is made in a microwave susceptor, a material that absorbs microwaves very well, and it doesn't melt like silicon carbide. So silicon carbide, it will heat really, really, it will be very hot. It will start to be red hot, and that will send infrared, so by radiation, into your metal, into ceramic or even metal, etc. So this is what is the hybrid microwave. So it's something that uses a outer wall that absorbs really well microwaves, and this can be applied very well to ceramics, can be applied to metal powders, but we don't really care about that because the metal absorbs, and it can apply obviously to the composites. So in terms of heating mechanism, once again, we have radiative heating for ceramics, either by hybrid or microwave plasma, and we have conductive and radiative for metal powders, and the same for composites. So what I read here what I wrote in red here, the microwave sintering species can interact both through the magnetic and electric forces. Do not forget that some of these metals, spheroids, for example, are they are magnetics, so magnetic field will influence upon them, and the same. So both of these, electromagnetic field can be used. So this is how we heat when it's about microwave sintering.
I have my own experience working with stainless steel powders because I brought our old microwave from my kitchen to work one day about 15-20 years ago because I wanted to try it. But I took our standard compressed parts, but I forgot that when we press and center, to press and have a high density and to have a long lifetime of the tool, you add a lubricant. So the material contained a lot of lubricant. So when I started to center that, something really happened. But when the temperature after a few minutes came up around 400-500 degrees, the lubricant started to burn, and it got very foggy in the lab, and people around me told me to stop playing with that equipment.
Sure. That's very understandable. Do you have an idea why that happened?
I did it in air. And having an organic material that starts to evaporate in air and temperature goes to 550, it just starts to burn.
Yes, that's it. That's exactly the answer. It's combustion temperature.
Yeah. So it was a big mess. But the funny thing was that when I took out the parts afterwards, they were sintered. They were even stainless steel in air. You cannot sinter that. It's people are crazy if they try to do that. But normally we sintering in very pure, clean hydrogen. But I couldn't put hydrogen into the furnace when I make these trials. But it worked. And when I could make such a simple test and make it work, I could see a potential in if people who knew a little more about it had this in their hands, for sure it could work.
Sure. it is, I mean, that's a very good example what we can and we can not do with the microwave oven. In fact, what you did is very good. But then, you should have done a little bit of a risk assessment around it. It's, the fact that your lubricant, the oil, burned, it's hot chemistry, it's nothing to do with microwaves, So yes, you can't put hydrogen through the oven, but you could have had an inert atmosphere like nitrogen or
Yes.
maybe argon, but nitrogen. So
Yeah.
it's not easy to do that in a kitchen oven because the kitchen oven is not leak proof, I mean, the kitchen oven is also high voltage.
Yeah.
And it's not the microwave oven itself, the cavity of the oven is not in fact leak proof gas or steam. And all these gases or even steam or conductive stuff, they can go to the high voltage. And at the end of the day, the safety point is not even microwaves, it's high voltage. And high voltage, we know high voltage, but nobody associates high voltage with a kitchen oven. Although it's kitchen oven, it's about 4 kilovolt in there, right?
Yeah.
Transformer, that heavy part, there is a transformer in there. And it is not done leak tight because, air needs to circulate around to cool down, the kitchen oven, the oven itself and the magnetron. So in terms of that, combustion, that's pure chemistry. Hot chemistry is nothing to do with microwaves, but it was fast. Okay.
Yeah, absolutely.
And this is, also something that we need to be aware with microwaves. We don't have a lot of time so we need to think about the experimental setup before doing it.
Yeah.
Right?
Yeah. As you said, the walls are reflective. And it just continues jumping around until it can get rid of the energy. So when you put in energy, it just continues until it hit the target.
Well, the kitchen oven is, as I said, is a little bit more clever than that. The walls absorb some of the microwave energy. It's magnetic metal inside, so they absorb a little bit because it was done for security. And there is another security on certain oven. You have a thermal snap on the magnetron. So if the magnetron gets hot because there is too much reflected power or hot air or whatever, it will stop, but you don't know because there is still light inside. I can hear my microwave oven. It's a very modern one. And I can hear when it stops, if I have something that makes a lot of steam inside, then I can hear when it stops, especially when you do popcorns and things like this.
Yeah.
If you overdo it, right?
Yeah.
So now, okay, we mentioned the kitchen oven, but I believe, this microwave sintering, in terms of giving us proper feedback, how to scale it up, we can do it in proper equipment, and there is equipment available there. We call it at both frequency 915 megahertz and 2.45 gigahertz, so the kitchen. Okay, 915 megahertz, just for you to give an idea, it's a much bigger oven cavity. If we had that at home, probably that would have been the size of a fridge or something like that, a big refrigerator. And I believe the history is that initially they put this really big, sort of microwave oven. Probably it was 915 megahertz. I don't know. I think so. I recall something. But basically 2.45 gigahertz was also done because it's much smaller in dimensions. Okay, it was closer to the radar. So we have the possibility to start our research in what we call the monomed resonant cavities. Now that the 2.45, this cavity, let's say in terms of how much powder I can put inside, right here. So I've done this little modeling. This is electric field, this is magnetic. I always need to put my sample right in the middle where the electric field is at its highest intensity. Okay, so let's imagine this is here right in the middle. This is the cavity, this is my sample. So the amount of sample I can put there it's something like, I don't know, let's call it 80, 100 grams, depending on obviously the density, the particle size, etc. While if we go to 915 megahertz, that can be a much bigger quantity. I can go even to, half a kilogram. So it starts to be quite important.
Yeah.
In terms of my microwave power, at 2.45 gigahertz nowadays for research and even industrial, we can go to 6, 10, 12 kilowatt easily. 915 megahertz goes up to 125 kilowatt. So
Wow.
we can build very, very important, sort of equipment around it. So this is something that we call a monomode resonant cavity. So what is called like that is because the microwaves, they go in one way and they come back in the same way if they are not absorbed. And what is important is that we measure this. So let's say I want to send 1 kilowatt into my sample. I put it in, I ask my microwave generator to give me 1 kilowatt. And at the end, I can measure if this 1 kilowatt was absorbed, then I will have reflected power 0. If it's not absorbed, I will have a value. And then I can either adapt the system so the power is absorbed inside, or if I still have reflected power, then maybe my sample cannot absorb all this power, and at that point I can lower it. What this is important is because at the end it will give me a power per quantity or energy per quantity. I will have a time, I will have the power, I have the quantity, so I can make the calculation how many joule or how many watt I need to process this quantity of material in this time, So this is it's a very simple installation to realize. We need to buy all these components are off the shelf, micro equipment manufacturers, they sell them, it's off the shelf, And then what I need to do is to control my atmosphere inside, okay? So not because I have microwave, it means that, the chemistry is not there. So I need to take into consideration also, do I need to make, like you said, do I need to put hydrogen? Do I need to make an inert atmosphere? Do I need some insulation around my sample because it will go to 2000 degrees, and if the sample is in contact with metal, then I will lose some of these calories, and the waveguide will be hot, and I will burn my fingers. So all of this, they need to be taken into consideration. And then we can do something similar to the kitchen oven, but let's do it a little bit better. In terms of the kitchen oven, we call it a multi-mode cavity. Is not a resonant because I said some of the power is absorbed by the walls and the turntable. But let's imagine that we have stainless steel that doesn't absorb, so 316L in here. It's all continuous. I can have either one single microwave generator, I can have two, I can have more, so I can get more power inside or more uniformity of power distributed. I can even have a turntable to put my sample onto. I insulate this sample with a material that keeps the heat inside, which is transparent to microwaves, for example. And then I can also make a hole in the oven to have inert gas, to have vacuum if I wanted to. I can measure the temperature. If I make an inert gas, I also need to exhaust it, but I need to exhaust it in a very controlled way, so not to have, toxic molecules coming out. So all of this is possible to do and is being done. And once again, it can be either 915 megahertz or 2.45 gigahertz. Both frequencies, we can do this. And lately, how can I scale up? Because that will be a question. Well, listen, I put a photo here. This comes from diamond making, what we call the lab-grown diamond making. These are reactors that are put, next to each other. So many reactors that run in parallel, each of them making, I don't know, 8 diamonds at a time. I'm not quite sure, what the size of the reactors. But basically, all of this can be either 915, 2.45 megahertz, gigahertz, and they can run in parallel. So what this can be, multiplied. And this is something very important for microwaves, because once you created a module, you can reproduce the same with no many changes, you know. So I'm a chemist, I'm an organic chemist, I'm an engineer, and I know that sometimes, building a pilot plant is just a pain because we consider it so expensive and it's got no value in the industrial process after. No, here we can build a module that can be reproduced and can work industrially.
Yeah.
Okay.
These are batch furnaces. Is it also possible to make it continuous?
They are batch furnaces, and I did think you would be asking this question. In my opinion, yes, you can make continuous processing, and will have to make continuous processing out of sintering, as well as many other high temperature processes. I have many other examples in my head, not to do with sintering. We will have to make them work in continuous processing. So at my knowledge, I might be wrong, but at my knowledge, is not done continuously nowadays. It's still done in batch. But I don't see, there will be a challenge to make it continuously, but it could be done, in my opinion. Imagine, this oven, it's got a conveyor belt inside, and this oven is not just for one sample, it's a little bit longer, and you have a conveyor belt inside, and you put your sample there, and, so each sample is contained in a compact in this case, okay? But who actually is, you can imagine these modules, with a hole in here and the conveyor belt going like that, and you have many, this is what we do usually in the industry, in drying, in food processing. It's exactly a conveyor belt that we use with 3, 4, 5 microwave cavities, and your product goes continuously inside. So I don't think this will be, a big problem. I think it's just materials, working at that high temperature and not losing calories. That is going to be the challenge.
Yeah.
Okay?
Yeah.
Right. So having all this said, I keep saying, it's just not just microwave sintering, but I actually adapted this slide to make it for the microwave sintering. When we do microwaves, we should not forget that we can, microwaves can be combined with other processes, what I call hybrid processes. So for example, if my ceramic doesn't absorb, I might want to preheat it before, because most materials, they change, the electric parameters with temperature. Some of them become more absorbent with temperature, right? I can also recover the heat from, I heat this material at 1,000, 2,000 degrees, and I also send an inert gas through it. Why don't I use the heat recovered from that gas to preheat the material? I can use vacuum, I can use inert or even reactive atmosphere. All of this is possible with microwaves, and it's important at some point to have this in our heads, because we talk about green processing and about, looking how much we consume, what's the carbon footprint of the process. So obviously this is all important.
Yeah.
Okay.
Yeah, but I could see, if we talk green, and if we talk the efficiency, if you have a traditional furnace, you heat up everything, and you have a lot of radiation, so your losses are radiation losses to the external. Here with microwave, you heat up what you want to heat, and the walls are not really heated; they're just reflectors.
Yeah, and that also, it's exactly one of the big advantages of the microwaves. And let's go to this slide then, but perhaps we need to discuss this, because I was also trying to answer, is it a green technology?
Yeah.
And there are 3 different parameters that I took into account. First of all, we are talking about fully electrified. So yes, microwave as a technology is fully electrified, because all these generators, magnetron based or solid state, they convert grid electricity into microwave energy. In terms of grid to microwave power, I also wanted to put these numbers here. You mentioned losses in a conventional oven because of the heat in the oven, but also if this oven is heated by gas, then you also have quite a lot of CO2 into the atmosphere.
Yeah.
But we have a grid to microwave power conversion, which is given by the magnetron and the power supply. And for a 2.45 gigahertz, it's not about the quality. This is physics around, okay, the magnetron. So the overall grid to microwave power. So how much power I need to convert from the grid to produce microwave? It's about 65 for 2.45 gigahertz, and today it's a little bit higher than 80 for 915 megahertz. So we have very important efficiency, electric efficiency for 915 megahertz. So also related to the highest power on the magnetron, I think 915 megahertz needs to be more investigated rather than kitchen ovens.
Yeah.
Okay. But yes, it's true, it's fully electrified with this very high electrical efficiency. But another parameter is that exactly what you said, that the energy is targeted directly from the microwave generator to the substrate to be heated. And we gave the example other than ceramics, is liquid, is solid, is gas, I form a plasma, it's straight in there, and it's a known number. I know this number. And I know if that's a good number, I can do my CapEx, OpEx, and I can do my return on investment. I can do all this model based because I know how much it is. I know how much I need to pay NG or whoever provides my electricity at the end of the month. I know all of these parameters. Okay? And third parameter related to the sintering process, in everything that I read, we have, and you also mentioned that, rapid heating rate. So we have something like 20 degrees reported per minute versus 5 degrees per minute in conventional. So that means it's faster processing time. It's 75% less time. That, of course, goes to reduce energy consumption and OpEx. Then it's been also reported that because of this very controlled way of applying energy, the sintering temperature can be decreased. I saw pure alumina sinter in microwave at 1,600, 1,750 degrees. Versus almost 2,000 in conventional.
Yeah.
There is lower environmental hazards, obviously. We don't burn gas, we don't produce CO2, and so, not directly anyway. And we have quite a lot of process control. We use in industrial ovens, we use as soon as you have a little alarm or a warning, you can stop everything immediately, and there is no inertia. Okay, there are nothing happening. You want to turn it on, you turn it on, microwaves are delivered immediately. There is absolutely no inertia in that, so that's important. And lastly, there are improved physical and mechanical properties reported, and obviously the possibility of creating new materials, which to me, is also very important. So I believe this is a little bit, summarizing the microwave sintering. Any questions you have? Happy to answer.
Yes, I do. If you have an efficiency of 80%, but if you have a 10 kilowatt system, you still have 2 kilowatt of excess heat in your magnetron. How do you get rid of that? Is it cooled?
Yes, it's water cooled and is not we use closed circuits for cooling. I mean the water for cooling the magnetron is not cold water, is not 4 degrees, it's something like 20 degrees. It needs to get, the magnetron is water and air cooled, very little air. At home you only have air. But in industry, this is not possible because, air can be different, temperature can be dirty, anyway. So the water cooling is the most important. So it requires closed circuit. And sometimes in the industry, the fact that the water goes at 20 degrees and comes out 23, 24, we can also recover some of the heat from that, depending on what we do. And I have an example of an industrial customer that requires that hot water for another process, okay, to heat up another process. So it's a win-win situation. Nothing is lost.
Yeah. Perfect. If we jump into this plasma talking, what is that? How does it work? Because plasma for me is you have a big voltage gap and you create acceleration of ions, and then you have a torch. But how does it work with microwaves?
I will try to explain in very simple. I mean, I can talk about it. This is one of my specialty. My expertise in microwave plasma as well. So I can talk about it for ages. But I try to also to summarize in 4 or 5 slides with some videos. And obviously, if there will be more questions, we can talk about it. So basically, when we talk about plasma, there is a lot in the literature, and I try to, here to the left, I try to give the definitions of plasmas. Basically, we can categorize plasma by pressure. We can do atmospheric or low pressure plasma. The type of coupling you mentioned, it could be inductive, capacity, then the generation, microwave, radio frequency, DC, AC, DBD, corona, hollow cathode, electron beams, torches, welding torch. And in terms of gas temperature, I think this is very important. We call low, or sometimes it's also called non-thermal, because the gas temperature is lower than 2000 Kelvin. To me, that's, quite hot.
Yeah.
This is gas temperature, is not even, electron. So it's gas, and we call thermal plasma if the gas temperature is higher than 2000 Kelvin. So I prefer I prefer the definition in terms of thermodynamic equilibrium. I know it's more scientific, but basically we have also 2 regimes. One is thermal, when in a plasma you have a soup, we call it a soup, of electrons, ions, and the gas itself. Everybody is at the same temperature, and we call this thermal. Or we call it non-thermal, or there is a mistake here. It's not thermal, it's equilibrium and non-equilibrium. I have to correct that. So we call it non-equilibrium if the temperature of electrons is higher than ions and gas, and equilibrium if everybody is the same. Very sorry, there is a big mistake here. Okay, so basically this is, a way to classify plasmas, but people are not very clear about it. Now, whatever we choose, I will choose my definition with thermodynamic equilibrium, so non-equilibrium or equilibrium. And then microwave plasma, they can be also equilibrium or non-equilibrium, and that's a little bit related also to the pressure. Equilibrium will be more low pressure, non-equilibrium will be atmospheric pressure. And I will explain why. So in terms of why we use microwave plasma, once again, if I go into this diagram, it's electric power only. So the same microwave generator that does your sintering can also do plasma. I mentioned 915 megahertz, 2.5 gigahertz. All frequencies create a plasma. We can have industrial application. There are industrial application and low and high gas pressure. Once again, very high process control, plasma on, off, exactly as I explained from the sintering, and the process is controlled. No electrodes. And I also mentioned the high energy efficiency, basically 915 megahertz, the generators are more efficient than 2.45. So all of this, yes?
Yeah, so no electrode means no
No,
wear, because that's typical what you see when you have
yes.
standard plasma. It's cheap to make and it's just electrical energy, but your wear and your maintenance of the electrodes is the costly part of it.
It's that, and also if you want to do, for example, processes where the electrode itself, the material of the electrode itself, would be a problem because the electrode wears, but everything goes into the plasma, right? So
Yeah.
if you have a reaction in there, then
Mm.
that is not very good, right? Because you have
Mm.
impurities coming there, and you have,
Yeah, exactly. Yeah.
So
Yeah.
so yes, you don't have any electrode in the plasma, in the microwave plasma. And once again, there are certain plasmas that can be only operated at atmospheric pressure. Here it doesn't matter of the atmosphere, of the pressure, most
Yeah.
of the time. So I worked quite a bit with low pressure plasmas some years ago, but most of my career I work with atmospheric pressure plasmas.
Okay.
So, and it's
Yeah.
just amazing what a plasma can do.
Yeah. On this the low temperature plasma, uh, I was wondering if you have nitrogen in a plasma, you typically produce a lot of NOx. Uh,
Not if you only have nitrogen. If you have air
yeah,
in the plasma,
exactly.
then
Yeah.
you
Yeah.
produce NOx. But if you have
Mm,
nitrogen,
yeah.
or pure nitrogen, you
Mm,
don't. It's an inert atmosphere. Nitrogen, we will see a bit later, will ionize. And
mm,
once you know that there is no microwave field, no nothing, no energy, then
mm,
it just cools down. It goes back to nitrogen. There is no reaction. Okay,
mm.
but yes, if you have oxygen in there,
Yeah.
there will be a reaction because the temperature
Mm,
is very high.
yeah. But can you make it so cold? Because I think it's if you're above 1350 degrees C, you create the NOx. But can you make a plasma that is lower than 1300 degrees C?
You can make whatever temperature you want, because here the idea is
Mm,
really you have all this power, the temperature will depend on two parameters. One is the gas flow, and the other is the how much power you put into it, right?
mm, yeah.
So if your temperature is too high, then you can lower the power, you can increase the gas flow, whatever you want,
Okay.
both of
Yeah.
them if you want, right?
Mm,
So,
yeah.
so the more gas you have, the less energy, right?
Mm,
It's just a question, and this is continuous flow. So the gas goes into the microwave
yeah.
cavity,
Mm,
it's transformed, it's ionized in there, and then goes out. And if there is no energy anymore, it just
yeah. So there's
doesn't.
not an initiation point that you have to be above before it starts.
Yes, let's go to the next slide.
Yeah.
So yeah,
Uh,
obviously, plasma, generally speaking, is formed when enough energy is sent into a gas to make it
mm,
ionize.
yeah.
So ionization, means energy. You create positive species, negative species. They are in equilibrium. Okay. So if you create it, so say argon here, I
Mm,
send 15.6 electron volt into the flow of argon. I ionize, I make a positive charge and an electron. This is
mm,
the condition.
yeah.
Nitrogen, it's exactly the same. I
Mm,
need enough energy to take at least one electron out of the molecule.
yeah.
Then I can do the same in methane. I can do the same in hydrogen. I can do the same in helium. There are
Mm,
many other gases, all I need is an ionization, enough energy to arrive at this.
mm,
Okay. Once I created that, the plasma consists, and this is very important to understand with microwaves. This is the main difference with microwaves. So once again, you create electrons, you will have some neutrals, atoms, molecules, in the soup. You have
mm,
excited species, so neither charged particles nor neutral particles, but just
mhm,
enough energy to keep them excited. You have ionized gas, excimers. When you create a plasma, you see light. Okay, so it's UV light in there as well. So all of this you form. Now, why microwaves are very important? I put this again, this thing here. And I mentioned when you have molecules, dipoles, or even ions, if they are heavy, they cannot follow the rotation of the electric field. But tiny electron is the only species which can actually follow the whole rotation of the electric field. What happens to it? Well, it starts to rotate like crazy because the electric field is there. It gains energy, and it cannot gain too much, so it will collide with neutrals, it will collide with molecules, and this collision could be either elastic, so it goes there, gives up energy, goes back to the electric field, or inelastic, it stays attached. Okay, so this depends on the pressure, elastic and inelastic collision. But this is the main difference of microwave plasma, is this electron that makes all the difference. Okay? So it's very energetic, and this is why microwave plasmas are electrical conductive, but electrically neutral. There is a quasi-neutrality. We call it the same number of positive and negative particles.
Yeah. So you don't have an acceleration field.
No. Like I mentioned, my accelerated electrons. No, you do not. It's just so. In order to explain this a little bit, I have a couple of photos here. So you mentioned, I will start with this one. These two are videos. So you mentioned air. So if you go air at atmospheric pressure, yes, you make NOx, and you can see it in the color of the plasma. Gases, when they ionize, different gases have different colors. So NOx is kind of clear here. It's the same color. And then argon at atmospheric or low pressure is this mauve color. Nitrogen is this mauve color as well. So this is argon at low pressure. So basically we create a vacuum, and then the plasma auto-ignites in there. We send microwave and there is auto-ignition. It just, we create a plasma. And I also have these two videos are at atmospheric pressure. And what I would like, I will start the video. So this is 2.45 gigahertz. And I showed you this photo and the NOx, which is formed because this is in air. It's a nitrogen plasma, but it goes into the air and it starts oxidizing around. So the color will change in my video. But also in this other video, I have nitrogen plasma, and then I start introducing some methane, and you will see the color change. Basically, this is to see the color change.
Yeah.
So I start the first video. So this is, I run the plasma and the color intensifies because I create more and more NOx around. Once again, this is in a extracted and ventilated fume hood with a lot of security in place.
Yeah, good idea.
It is not in just on a bench.
It's not in the kitchen.
No. These are very specialized reactors. And then I would like to look. So I contain this plasma in this metal cylinder, and then I put a window here, and I introduce the methane, and look how the color changes.
Yeah, wow.
Right? Okay. Basically, this is, there will be hydrogen, there will be some nitrogen in there, there will be some carbon, so you will have some radiation from the carbon as well. So this is about plasma. I will go here in terms of how we create this plasma. It's exactly the same equipment that we use for the sintering. So the same microwave generator I put here is the closed circuit water cooling. The same microwave transmission line, which is in tuning of the power. So waveguides, metal waveguides, which are standard. And then I have a microwave plasma source. That's what you saw in the videos. Okay. And this can be either separated through a window from my plasma reactor, or can be directed straight into the reactor. If it's atmospheric pressure, okay, then it will be, there is no window, but obviously if I need to create vacuum inside to go to lower pressure, then I have a pressure pump, and I can create primary vacuum or even very, very high vacuum inside, and I can create plasmas at any vacuum condition. Okay.
Yeah. How high power level can you reach with such a microwave plasma system?
Per unit, it depends on the frequency used. I mentioned 10 to 12 kilowatt for 2.45 gigahertz and 125 kilowatt for the 915 megahertz. I don't know many people using the 125 kilowatt. It's been quite recent, but it's 100 kilowatt. I know it exists in the industry.
It's a lot.
It's a lot. And mind you, I will mention this a bit later in terms of oxidizing air or creating a plasma in air. I'll mention this later as a very, very interesting application. Okay? And then in terms of the application, where microwave plasma are applied today in the industry, we have some of this high temperature heating for application in industry with high energy consumption, like kilns and furnaces. Obviously, chemical synthesis, I mentioned the gem and technical diamond synthesis. This has been, something so important to the whole industry for the last few years. A lot in nanomaterials, a lot in ozone formation. We can form very easily ozone with plasma. And then a third application is metal processing. Material processing, with thin film deposition, is very well known in the semiconductor industry, coatings, optical device fabrication. Also surface modification.
Kind of PVD?
Exactly that, plasma, chemical enhanced vapor deposition and plasma, So surface modification to enhance material properties. We mentioned some in the sintering, hardness, corrosion resistant, adhesion. We forgot to mention that in sintering it's also a term for joining different ceramics together. We use different that also microwaves to do that adhesion here. And very, very new and in environmental application, we talk about power to X. So that means producing, for example, hydrogen with less CO2, what we call the CO2 neutral, no carbon footprint. And power to gas, so producing syngas via methane and CO2 reaction, rather than producing with steam methane reforming and things like this. And gas abatement, air purification. We also have microwaves. I work quite a bit. I mentioned for Edwards, BOC Edwards for gas abatement using microwave plasmas. And then we have all sorts of emergent application in biomedical, cancer ablation, sterilization. We can do with microwave plasma. With very low power, we can do very, very precise application of microwave plasma for sterilization or even for cancer ablation. And space exploration is something that I read. There was another application, propulsion. There was another application here, in terms of environmental application, and that is making fertilizers directly by putting air, oxidizing air, producing NOx, because fertilizers are based on nitrates. So if you produce NOx, NO2 and NO molecules, and then you produce nitric acid, then you can produce your nitrates without going through the whole chemical process. So this is also, I will mention in these slides, in this scale-up strategy, because this is the question that I get very, very often. The industry doesn't need just 100 kilowatt to make, a big reactor. It needs a lot more. And one of the microwave manufacturers, I shouldn't probably given this, but he gave me the permission to publish this photo. I believe it was also on their website, where they can put, this idea of modularity I explained to you, which we always said. So they put multiple microwave generators in containers. that offers mobility. And then out of it, you can have multiple reactors, be those plasma or sintering or whatever you want. It could be done like this. The advantage of this is that if you have an ATEX zone, especially in all these chemicals, hydrogen, methane, etc., then everything to do with high voltage is in one generator, or it's enclosed, and you have your chemical process in a different container that you can make ATEX. You don't need ATEX in here, but you can. So that will cost a lot less to make an ATEX only in the chemical process itself. Okay, so I mentioned natural gas pyrolysis for producing carbon and hydrogen. Also, acetylene synthesis is done. So this is atmospheric pressure. Acetylene is done at lower pressure, primary vacuum, and then fertilizer from air. And I gave the name of a few companies that are also online. Saco in Green Energy in France, they look at carbon and hydrogen production. Transform Materials in the United States look at acetylene synthesis, and nitricity at fertilizers. So that's one way of doing this, is by putting multiple generators in series. You can also put them in parallel, and I gave this example with multiple reactors, individual reactors. There is a lot of, in this modularity, there is a big advantage. The advantage is that, say you have production and one of your reactor or generator breaks, and everybody else can run. You don't need to stop the whole, machine because so you might need to lower a little bit your throughput, but you don't need to stop. And this is a big advantage. Or if you need to stop,
that's typically what happens with big industries, depending on everything.
And I think, it's, to be honest with you, this is seen as a high capex, sort of, because putting so many generators, high investment in the equipment. But then, in my experience in the industry, there are so many business models, and they are based on capex, but less on opex, and also the return on the ownership, cost of ownership. And I think a good economic model should take into account all of this, but there is not enough information out there. So hopefully with your help, we can pass a little bit more, and I'll try my best to pass a bit more of this information all the time. I think this is it. I think this concludes my presentation. I will stop sharing. Okay, that's it.
Thank you very much. I learned a lot, and I didn't know that there were these activities in such big machines on industrial scale today. So thank you very much for sharing.
It is still a niche industry. There are still niche markets. Probably the most well developed is still food. Both processing, so that means defrosting, we call it thawing, bringing from minus 20 degrees to about 0 degrees. That's an important business. It's a lot of drying is being done with microwaves. And again, in these processes, we don't want only one process. Usually it's 2 or 3 more processes. For example, drying could be associated, if it's about food drying, it could be also associated with pasteurization, insect sort of contamination by insects, also removal. So most of the time we look at more than one. In the chemical industry, we also look at one-pot reactions. So for example, you have a solid solvent, you put it in your reactor, you put everything else, but you apply microwaves. The first you will melt your solvent, and then you will start the reaction, you see. So it's one pot. You don't need too many sort of stages for that, or adding a little bit of this and a little bit of that.
Marilena, at the end of our talk, you mentioned that you were going to conferences specific on microwave, and I could see that as a potential where to learn more. Could you share a little of where that could be? Are there associations, or how is
Yes.
the microwave society built up?
The Microwave Society, there are two main, there are many important groups, but I'll talk about North America and Europe.
Mm,
So basically, there is an association of microwave, and it's international. There is Japan, there is China, there is India, there is North America and Europe. So there is this big association. I know very well Ampere. Ampere stands for Association for Microwave Power Education and Research in Europe. And we organize, and the one in North America is called IMPI, International Microwave Power Institute. They've been created many years ago
mm,
by people who some of them are not among us anymore, pioneers of microwave application and radio frequency. Some of them are still with us.
yeah.
And they organize conference. IMPI is more like a symposium. It's every year and it moves in North America.
Mm,
So this year was in June in Edmonton, Canada. Next year, I can't remember that they
mm,
decided. I didn't go to Edmonton. There was something else going at the
yeah.
very same time.
Mm,
But in September of this year, from 15th of September, so in 2 weeks, we are organizing Ampere 2025, which is the conference of the Ampere Association. And this is a conference that we organize every 2 years. And this year, there is an important day that we organize. We call it Industry Day. So if you go to Ampere to 2025.org, okay, so this is the link of the conference. You
yeah.
go to the program, there is a day dedicated to the industry application. And what we wanted to do is to bring end users,
Mm,
so people from the industry who use microwaves either for heating or plasma, to
mm,
talk about their application. It's
yeah.
probably I tried this some years ago in Toulouse. It's many years ago in Toulouse. It was only half day,
Mm,
mostly to do with cosmetics. They use quite a lot of microwave in cosmetics, but quantities are a lot smaller. So,
yeah.
but this year we organize this industry day. It's one day, no other sessions in parallel, and it's really dedicated
Mm,
with the industry. And there are 3 more days dedicated to science.
mm,
And a lot of presentations. So feel free to go to the program of the conference, and you can always come there and
yeah.
assist, pay your registration,
Mm,
and assist to the conference, or even for the industry day you can do 1 day registration.
mm,
So it's a
yeah.
full day from 8:30 in the morning until late in the evening.
Perfect. I'll put a link to that in the notes below the podcast episode.
I will give this in the chat. So the Ampere conference.
Perfect.
Ampere 2025. And this year is organized in Bari, Italy, which is southeast of Bari. Okay. So I sent it to you in the
Yeah.
chat.
Perfect.
Okay.
Thank you. Yeah. I am filled up today. My head is about to explode, and I cannot take any more.
I know. This is why I thought a little bit, do you really want plasma as well? Because
Yes.
it's that these are very big subjects, both of them, sintering and plasma.
It is. But
Yeah.
thank you very much. I really enjoyed it.
Thank you for inviting me and for making this possible. And I look forward to the podcast.